everyone. I am Manu Ramesh, and today I'll be explaining what Eidetic is, and I'll be presenting our work, Eidetic recognition of cattle using keypoint alignment. So first of all, why do we have to do cattle recognition? Cattle recognition helps us monitor health of individual cattle, their milk production, track their disease transmission, their behavior and ownership records. And it's a bonus if it can be automated, if it can be run by a machine. So everything that is listed above can run very fast. An example of automatic recognition can be seen here. Existing approaches for cow recognition or cattle recognition in general include physical methods such as branding, tattooing, ear notching, ear tags. The problem with these methods are they're intrusive and they're not machine readable. Electrical methods include those that use RFIDs, and these are also intrusive, and on top of that, they're expensive. Of late, many computer vision techniques are being developed. These identify cows by identifying the pattern on their backs and their faces. But the problem with deep learning is they need to be retrained every time a new cow is added to the set, and they just need too many training samples. So what's our problem statement? In an ordinary dairy setting, there will be new cows that keep coming in and keep going out. So we need a system that can recognize a cow with minimum training data, and it should be able to be retrained in very minimal time. So here's the idea that we started with. So we took an image of a cow in the top view and started squinting. So these images look pixelated, and we thought, what would happen if we binarize these images, and what do they look like? Well, to me, they look like QR codes. So if we take an image of a cow and convert it to something like this, they can be stored as bit vectors that can be used as feature vectors for the recognition. So now I'll tell you how we created the cattle log. So the data collection, curation, and the data set creation. To collect the data, we set up two top view cameras in the Purdue dairy, one in the barn. This is an example of a barn image, and one in the holding area. So we can see that there are multiple cows in an image in the barn, and we collected data over different lighting conditions. And in the holding area, one cow passes through a set path, one at a time. So all of these cows pass through. So from all these data, we took the data from summer 2022 from the 2 days, cut the videos to one cow per video to create the training and testing set, and together they form the cow videos data set. And we sampled one image per video from the cow videos data set to get our cow images data set. We created yet another data set called the cow keypoints data set. We took those data bracketed there, and then we sampled images from the data, annotated the keypoints and masks like this, and then we create the training and testing set of the cow keypoints data set. So in the cow videos and images data set, we have 153 cows in the train set, 170 cows in the testing set. In the keypoints data set, we have 893 images. Note that these images can include multiple cows in a single image. But the 170 images here and the one in orange in the cow image data set, they are the same images. And the keypoint detector has not seen 11 cows during training. So from the cow images data set, the train set, we took the 153 cows. We used the keypoint and mask annotations to obtain images like that. Some issue here. We took the images like that, and then we grayscale, pixelated, and thresholded the mean to obtain images like this. So these are the pixelated binarized cow cropped images, what we call the catalog, or the set of known cows. They can be stored as bit vectors. And now I'll talk about a method. So cow recognition is localization plus cow ID prediction. we divide the recognition into these two parts. So how do we predict the cow ID? We take the pixelated image and then we serialize it to obtain our instance bit vector, just as I explained before. And we take all the images, the bit vectors from the catalog, and we use nearest neighbor matching, and then we use Hamming distance to get our predicted cow ID. But how do we localize these cows in the images that are like those from the top view cameras? We extract the mask using mask RCNN, and then we use the mask RCNN to obtain the rotated rectangle bounding box. And from those boxes, we use the mask to remove the background, and then from the rotated bounding box, we crop the image to get just the cow, and then rotate it to vertical view to get images like those. And then there's a problem with using just the mask. You see the cows are not great posers, so we get images like this, and they're having inconsistent orientation, and that leads to different bit vectors being generated, which in turn leads to wrong cow ID predictions. How do we solve this? So to solve this, we use key points, and we detect some landmark points in the cows, and then from these points, we partition the cow image into triangular regions, and then we affine morph each triangular region into a template that we design. And this template is defined by fixed cow size and fixed key point locations. And then we obtain a template aligned cow image, something like this. Note that all the cows in the catalog are also aligned to the same template. And to detect key points, we first identify 10 easily identifiable points on the cow's body. And these are the points. There are the spine points, the hip bones, tail bones, and the shoulders. We use Keypoint RCNN with two backbones, Resonate 50 and Resonate 101. And the backbone is shared with mask RCNN. So we just train once, and the same network detects both the mask and the key points. There are more problems with the key point detector, as the key point detector we use, Keypoint RCNN, is not perfect. So one such problem is misplaced key points. So here you can see a key point that is misplaced. This leads to wrong triangular regions, and that leads to wrong alignment and wrong prediction. So to solve this, we use key point rule checks. We crafted 21 rules to tell if an instance that is detected is a cow or not. These rules are based on heuristics. They could be rules as simple as checking the length ratios between two key points, if they fall within a threshold or not. And we consider a cow for rule checks only if all the 10 key points are detected, and we consider a cow for prediction if all the 21 rules are passed. So even if the cow instance fails a single rule, we drop it and we won't let it reach the prediction stage. Here's an example rule check. So here the ratio of lengths between the orange and the blue lines is roughly equal, so it's close to 1. So we say the rule is passed. But if, for example, the key point is detected here, the middle one, the ratio greatly exceeds 1, and we fail the rule and drop the cow from prediction. There's yet another problem with the key point detector, that is missing key points. Here's an example where the left shoulder has a key point missing, and we wanted to see if this trend persists in the entire training data set, and we plotted this graph. And in this chart, you can see that there are multiple instances where just 8 or 9 key points are detected. So the cow instance is dropped from the rule checks, and it won't even reach the rule checks, so it won't even reach the prediction stage. So how do we solve this? If we can somehow interpolate these 1 or 2 key points, we can push the cow forward through the pipeline. So solution is key point interpolation. We use the redundancies in this structure to interpolate key points, and we use handcrafted policies for interpolation. Here's an example where the hip connector is missing, and to interpolate this, we try to join the spine line and the line joining two hip bones, and then we use the point of intersection here as an interpolated key point. So we have similar policies to interpolate most of these key points, and some key points need to be detected, obviously, to interpolate other key points. So with this, we can push the cow towards the rule checks and then further to the prediction stage. So with adding these components to the block diagram, we add the cow key point extractor, the interpolation rule checks, and the cow skeleton alignment system on the bottom left. And with all these blocks added, here's the complete picture of the entire block diagram. And counting the numbers, here are the results. There's an important question that needs to be asked. Should the key point detector that uses deep learning, should it have already seen the cows for this to work? We plotted this graph where for both Keypoint RCNN that uses ResNet 50 and ResNet 101 backbones. On the x-axis, you have the number of Keypoint rules that are passed. On the y-axis, you have the proportion of all the instances in the dataset that are passing these number of rules, the given number of rules. And blue lines is the unseen cows, and the orange lines are the unseen cows. You see that the unseen cows, the plots of the unseen cows trace that of the seen cows nearly, so they have similar performance. This proves that the key point detector can work equally well on unseen cows, on those 11 unseen cows that I spoke about earlier. And here are the top K accuracy results on our cow images dataset. You see that the top 1 accuracy is 30%, and the top 16 accuracy never goes much beyond 50%, and this is not good. So we thought of what could be the reason for this. What's the bottleneck? Is it the prediction stage or is it the localization stage? And we thought of using the ground truth annotations, the key points for localization, and testing just the prediction stage. So we did that, and we plotted the max prediction stage accuracy using the key points from human annotations. And with that, we have these orange lines, and you see that there is a huge gap between the blue line and the orange line, and we wish to push this more towards the orange line, and this reaches 100%. So it's an issue with the localizer, not the predictor. So the reason for this performance gap, we came up with this hypothesis that the key point detector is not getting images in the ideal pose for this to work. So as a solution, we thought of running the recognition system, the entire system, on not just one image, but on multiple images of a cow and taking the majority vote. So we run it on a test set of the cow videos dataset instead of the cow images dataset. So we run the recognition system on an entire video, get predictions from each frame, and take the majority vote to be our final prediction. And the kth most frequently predicted cow ID for a given cow video is used as the kth prediction to compute our top K accuracy. So from this, we get the green plots, the top K accuracies on the cow videos dataset. We see that it's greatly improved, it's more than doubled. And you see that there are only 4 points in the ResNet 50 plot and 7 here, which means that the key point detector, the cow ID predictor is not getting confused beyond 4 different cow IDs for a given cow in the ResNet 50 model. When using the ResNet 101, the same is 7. So when we compare our results with those of Gao et al., that's a paper that's implemented on an entirely different dataset. It's not our dataset, so it's not a one-to-one comparison. But we can see here that we are achieving similar performance, and here are our results. We achieve this on a dataset with roughly the same number of cows, and using only one image of a cow, one image of each cow for training. So whereas they use images in the order of 100 per cow. And in conclusion, we build a system to localize and identify cows by their cow IDs. And this system performs similar to those based on deep learning without the need for lots of training images. We do this by splitting the recognition system into a localization system that is cow ID agnostic, that comes pre-trained, and a prediction system that requires just one image of a cow, one image of a cow for it to be trained. That's why we are calling this Eidetic. So Eidetic means you see once, you remember. And future work could include considering training the key point detector on interpolated key points as self-supervision and automatic catalog generation, etc. And here are our key references. And moving on, thank you. Any questions? Yes.
So, in one of your plots, you plotted on the vertical axis a percentage of instances that pass the rules, and if you go up to 21 rules, it sounded like it was under 10%. So that's a pretty small yield.
we'll get to that. So, if you remember how the cows were walking through the set path, you can see only a part of the cow in the beginning and a part of the cow in the end. The entire cow is visible only in a small window of duration. So that's when most of these rules are passed. When the entire cow is not visible, no rule is passed. That's why the 0 is a very high number. And this is low because we are pushing many key points by interpolation and they're passing most rules.
Okay, so for any given cow, the chances are very high that you'll at some point be able to see all 21 rules will pass.
Yes.
Okay.
Any other questions? Yes.
Initially when you were showing like video of cows, you were converting into binary format like QR codes as you showed. What happens if there is no kind of like pattern on a cow, right? What happens in that case? Because all the
That's
cows
an interesting question. We have such examples in our data set where the cow is completely white or the cow is completely black. And we are trying to match our performance with any ordinary human. If a human is able to distinguish a cow image or not, we are trying to get there. And in the future, we could consider using more features of a cow, such as the length, width, etc. And we can supplement this with that and then probably improve our prediction. Yes.
For your pose detection, is that the entire image or is it constrained based off of, because I'm assuming that the cow doesn't move its joints like a pose estimation.
Oh, it moves. It moves. It's
how far do the joints move?
So, if you remember the anatomy of a cow, towards the bottom, those 6 key points that I showed you, they remain fairly rigid, and towards the top, the shoulders, they move a lot. So that's the reason why there are so many rules that are failing, because our key point detector fails to detect the shoulders. And the camera is also off by a bit, so it's looking not directly down, but by an angle. So there's an offset. So sometimes you don't see some shoulders. So you'll miss key points, and that will also create wrong predictions. Yes, sir.
Questions are these the patterns that cows have. Is it like a fingerprint, or it's a very unique for cows, or you can have like multiple cows with the similar patterns?
I am not sure, but there in our data set, so we used the 16x16 block size for a reason. So we tried block sizes that are bigger, and then we tried to cluster. We tried to see how many cows had the same bit vectors that were being generated. So if I use 128x128 as a block size, there were multiple cows that fall under the same bit vector. But then I started reducing the block size, and for 32 there were around 7 clusters of cows that had same bit vectors. For 16 they become unique. So it's a trade-off between compression, data compression, and being able to uniquely identify cows. So with this we have 256 cross 512, and 2 to the 256 cross 512 is those many cows can be actually stored. So this system has a lot of memory, and cows could have similar patterns if we use a higher block size.
If the shape of the cow changes, like if the cow grows up, how does it work?
So we can still detect it because we are detecting key points, and then we are resizing all cows to the same template. So it works irrespective of orientation, irrespective of lighting, irrespective of size and angle of camera.
Okay, next faculty speaker.